Hello everyone, welcome to the online lecture series of the course EE204 Digital Electronics and Logic Design, Module 5 Synchronous Counters and State Machines. Today we are going to discuss about a synchronous modulo n or mod n counter. We have already seen what is a mod n counter. A mod n counter means the counter will be having reduced number of states. That is, if a counter is using n flip-flop or if the counter is n bits, the maximum number of states the counter can count is 2 raised to n. So, if the counter is counting states less than the maximum count, the counting sequence will be a truncated sequence, and hence such counters are called as modulo n counter or mod n counter. The design procedure for a modulo n or mod n counter is same as that of a synchronous counter. We have to follow the exact steps. The only difference is that here, as the number of states is less, the invalid state we need to treat as don't case at the time of designing. So let's take the example of a synchronous mode 6 counter. A mode 6 counter means it will be having only 6 states. So in order to count these 6 states, we require a minimum of 3 flip-flops. The counting sequence will be like this, starting from 000 to 101, and it resets to its initial state and the counting pattern will continue. We are going to design this counter using a JK flip-flop. So you can see the excitation table of JK flip-flop on the left side. On the right side, you can see the state diagram. Since the initial state of the counter is 000, starting from that we'll be having the 6 states 001, 010, 011, 100, 101, and finally resetting to the initial state 000. The two invalid states 110 and 111. Those two states are also shown in the state diagram. The purpose of that will be explained at the end of this presentation. So let's continue with the design procedure. So prepare the design table. So here you will be having 6 rows, each representing the states of the counter. So completing the present state, column 000 in the first row, 001 in the second row, and like that 101 in the last row. Now complete the next state column. If present state is 000, next state is 001. If present state is 001, next state will be 010, like that. If present state is 101, next state will be 000. Comparing the present state column and next state column of each of the flip-flop, complete the excitation required for the corresponding flip-flop using the excitation table. Since here we are having 2 invalid states for this counter, so we need to treat those 2 states as don't care terms in the design. On the left side, we can see the K-map for JA. On simplification, JA is obtained as QBQC, and on right side, you can see K-map for KA, and on simplification, KA is obtained as QC. On the left top, you can see the K-map for JB. On simplification, JB is obtained as QA bar QC. And on the right side, you can see the K-map for KB, and KB is obtained as QC. On left bottom side, you can see the K-map for JC, and simplification JC is obtained as 1. And on right side, you can see the K-map for KC, and on simplification KC is obtained as 1. And using this minimal expression for the flip-flop inputs, we have to complete the logic circuit diagram. And the completed logic circuit diagram is shown on the upper half of the slide. So now to have a better understanding of the mode 6 counter, let's have the simulation. You can see a similar circuit diagram as shown in the previous slide. Here, in addition to that, we can see 3 more switches in between the connection from the preset input to each of the flip-flop. This is to manually set each of these flip-flops separately. The purpose of that will be explained later. Now let's start the simulation. So checking the asynchronous inputs first, making the preset to 0 will set all the flip-flop, and making the clear input to 0 will reset all the flip-flop. Here the first flip-flop output QC will be the MSB, and the last flip-flop output QA will act as the MSB. As you can see, input to the first flip-flop is J and K both equal to 1. This flip-flop will be always working in the toggle mode, which means for each clock pulse, that flip-flop output will be just the toggle value of its previous output. So initially flip-flop output is 0, also on the next clock pulse this flip-flop output will become 1. For the second flip-flop, the J input is the output of this AND gate and its inputs are the output of first flip-flop and the complemented output of last flip-flop. Since output of first flip-flop is 0, the AND gate output will be also 0, which means the J input for second flip-flop is 0. Similarly, K input is also 0 as the output of first flip-flop is initially 0. The J input of third flip-flop is the output of this second AND gate whose inputs are the outputs of first and second flip-flop. Since first and second flip-flop output are both 0, the AND output is also 0, which means J input is 0. Here the K input is also the output of first flip-flop, that is K is also 0 here. So the first flip-flop will toggle its state whereas the second and third flip-flop will continue the present state. So we can apply the first clock pulse. So application of first clock pulse, the output becomes 0 0 1. So likewise you have to analyze the flip-flop inputs J and K before giving each clock pulse and correspondingly you have to observe the output. So on second clock pulse the output becomes 0 1 0. At the end of third clock pulse the output becomes 0 1 1. At the end of fourth clock pulse output becomes 1 0 0. At the end of fifth clock pulse output becomes 1 0 1, which is the last state of the counter. Then upon giving next clock pulse the flip-flop output resets to its initial state 0 0 0. This completes one cycle of the counting operation. In the state diagram, I have already shown all the 8 states, out of which 6 are in the loop and 2 are connected serially to the starting initial state. So the states 1 1 0 and 1 1 1 are the invalid states of the counting sequence. I have already discussed about the concept of lockout in the previous lectures. The unused state of the counter may sometimes act as the lockout condition for the counter, which means if any of these counter initial state become invalid state, the counter will not return back to its valid states. So let's see whether this lockout condition is present here. So the table to check for lockout condition is as shown in the slide. The first set of columns will be for the present state, the next set of columns will be for present inputs, and the last set of column will be the next state. So present state, you have to write the 2 invalid states in each row, and based on that present state and looking into the circuit diagram you have to complete the present input, and based on the present input and present state we have to complete the next state columns. So let's see one by one. Present state is 1 1 0. So let's see the present inputs. Since J and K of first flip-flop is connected to high, JC and KC will always be equal to 1. Since K input of the second and third flip-flop is connected to the output of first flip-flop, their value is also 0. That is KB is 0, KA is 0. The output of the AND gate will act as the J input for the second and third flip-flop. Here one of the input for the AND gate is the output of first flip-flop. Since it is 0, the output of AND gate is also 0. So we don't need to check the second input of the AND gate. So here JA and JB is also 0. So now complete the next state column. If QA is 1 and JA and KA is 0 0, then the next state of QA will be same as the present state itself, that is 1 itself. Similarly for the second flip-flop also, since JB and KB are 0 and since QB is equal to 1, QB plus 1 is also equal to 1 itself. For the third flip-flop, JC and KC are both 1 and since QC is equal to 0, QC plus 1 will be equal to 1. Similarly, completing the next row we can obtain for present state 1 1 1, the next state will be 0 0 0. So coming back to the simulation, now we have to check the lockout condition. We have already seen that if the present state is 1 1 1 on the first clock pulse, it will be returned to the initial state 0 0 0. Similarly, if the present state is 1 1 0, on application of first clock pulse it changes its state to 1 1 1, and on the second clock pulse it changes its state to 0 0 0. So both the invalid state will return to the initial starting state after 1 or 2 clock pulse accordingly. So let's set the initial state state as 110. So in order to set the state as 110, I am going to open this switch for the preset input of the first flip-flop. So now only preset input is available to the second and third flip-flop. So upon making the preset input to 0, the second and third flip-flop will be set to 1. Now you can change back the preset to its normal resting value 1. Now application of first clock pulse, the flip-flop output changes its state to 111, and application of second clock pulse, the flip-flop output changes to 000, which is the initial state of the counter. Now let's check the second lockout also. If present state is 111, on application of first clock pulse, the output changes to 000. So from the table to check for lockout condition and from the simulation also, it is clear that there is no lockout for a mode 6 counter. Whatever be the initial state of the counter, after 1 or 2 clock pulse, the counter will return to a valid state if the initial state is an invalid state. Now let's check the timing diagram. Here you can see initial state is 000. At the end of first clock pulse, output changes to 001. Like that, at the end of 6th clock pulse, output changes to 000. Here you can see that observing the timing diagram waveform of the MSB flip-flop, that is QA. Here for the first clock pulse, output is 0, and for the next 2 clock pulse, output is 1. So which means that duty cycle of this waveform is 2/6 or 1/3. One more thing you can infer from the waveform is that the frequency of the QA output is 1/6 of the clock frequency as expected in a mode 6 counter. So I hope with this explanation and the simulation works, you are familiar with the concept and working of a mode 6 counter.